In ice, the water molecules are basically fixed in place. They form a crystal lattice, where their only motion is vibrating. So what happens if we heat up the ice? So in liquid water, the water molecules not only vibrate, they can also rotate and slide past each other. And this is what allows the substance to flow. At even higher temperatures, the water molecules become free of that liquid and turn into water vapor. In that state, they are very, very far apart and moving very quickly. So the major differences between solid, liquid, and gas are the motion of the particles and the distance between them.
But even in water, such as this cup of ice, there's something different about the molecules. See, in the cold ice water, the molecules move very slowly. Here's my fish tank. My fish tank's at room temperature, and when we look at the molecules inside the fish tank, we see that these molecules at room temperature are moving significantly faster than those in the cup of ice. Now here's a cup of tea that I just poured from my teapot. The molecules in both of these are moving quite fast right now. But there's something different about the teacup and the teapot. I took the temperature of the water in the teapot, and I found that it was the same as the temperature of the water in my cup. But if I were to put the cup on the stove with some water in it, and the teapot in the stove with some water on it, the teapot has much more water in it and takes much more heat or energy to be added to it to get it to the same temperature as that smaller cup of tea. So the temperatures of each vessel are the same, but the energies required to get them there, the heat, is different. So in the simulation of the different liquids, you saw the jiggling molecules of the atoms. So you see that as the molecules jiggle more, they'll have more kinetic energy. And the more the kinetic energy they have, that kind of means the larger temperature they have. So average kinetic energy is directly related to a property's temperature. So when you look at the simulation, the higher temperature water molecules are moving at a higher velocity, thus giving them a higher kinetic energy. When we talk about temperature, we are measuring temperature in a couple different ways. We're not actually going to report temperature as the average kinetic energy of one of those molecules. We report temperature using a degree scale. So we'll report temperature either using Celsius, Fahrenheit, or Kelvin. And the conversions are listed here. It's convenient to use Celsius and Kelvin because the degree change is the same. Well, when we switch from Celsius or Kelvin to Fahrenheit, the degrees change different amounts, 1.8 degrees. Right? 1 degree Celsius is 1.8 degrees Fahrenheit. There's also a different starting point for Celsius and Kelvin. Kelvin goes from 0 on upward. Well, Celsius can only drop down as low as negative 273 degrees, which corresponds to absolute zero, the lowest temperature that any individual molecule can be. This is because there is a point when there's literally no kinetic energy of the molecule, zero velocity, and that is what's called absolute zero. So temperature is the measure of the motion of a molecule or atom within the substance and its kinetic energy of a specific molecule or atom. Now, when you go to the teapot and the cup, they might have the same average kinetic energy. So this molecule in the teapot and this molecule in the teacup might have the same velocity and mass and thus kinetic energy. But to get every single one of these molecules in the teapot to the same temperature is going to take a lot more energy because there's just more molecules. So heat relates to how much energy is required to get all of the particles to have the average kinetic energy that corresponds to the temperature. Let's just practice moving back and forth between degrees Fahrenheit, degrees Celsius, and Kelvin. So if you want an answer in Kelvin, you can bump up your degrees Celsius, by 273 degrees. If you want to change your Celsius into Fahrenheit, then you'll need to change the degree factor, so 9/5 of the Celsius measurement, and the starting location plus 32. So we can try that for a couple examples here. Notice there's some blanks that we're just kind of expect you to know. So ice melts happens at 0 degrees Celsius, and ice and water boils is at 100 degrees Celsius, and that's how the Celsius scale is defined. Now that turns out to be a little different for Fahrenheit. Who knows how he came up with that? But 32 goes here, and 212 is our boiling point for Fahrenheit. So go ahead and work through the conversion table. Pause here, this is in your packet, and check your answers when you're done. Here's your table filled out with the answers, so you can check anything you want. Mercury freezes, pretty cool. And knowing these numbers, 273 and 293 for room temperature and ice melts, is pretty helpful for future calculations. Also, just out of curiosity, it might be worth looking at how close to absolute value we've gotten in a laboratory.